Hello, everyone. Welcome to webinar number 9, AM Smart, Advanced Manufacturing of Smart Materials and Structures. Another session on shape memory alloys, favorite topic of this group and let's say this community. For today, we have Dr. Othmane Benafan. Othmane is quite well known in the field of shape memory alloys. And if you don't know him, he is from NASA Research Center in the United States. And he kindly accepted to host this meeting. We have two nice speakers and two different topics, both related to shape memory alloys. So I hope you enjoy the webinar today. And I would like to hand over the meeting to Othmane.
All right, thank you very much, Mirshat. Hello, everyone. Good morning, good afternoon. Thank you for being here with us this Wednesday. It's great to be alive. We have a great program for you today on a topic that a lot of people touch and some people live by. So it's whether you are new to SMA or seasoned to shape memory alloys, I think the topic of standards applies to all of us. So with us today, we have the pleasure to hear from two distinguished speakers. We have Dr. Doug Nicholson from the Boeing company, who have led several shape memory alloy endeavors. And related to today's topics, he has been leading the standards developments related to actuators, as he will tell us in a little bit. Our second speaker is Matthias Frotscher. Matthias is a senior manager of stint and materials testing in Cortronik GmbH in Germany, and he is also going to tell us about standards from a different perspective from the medical side. So we can cover both things, and really the goal of today is to highlight what has been going on in the community, both the old things that has been published and new things that are under developments, and how the two pieces of actuator and the medical aspect of standard developments match and shake hands, and to make the community aware of where you can find the information, how perhaps you can join the group if you're interested. And I'm excited to hear from both of them. So our first speaker, Doug Nicholson from the Boeing company, the floor is yours.
Yeah, thanks very much, Othmane, and thanks for inviting me to this group today to be able to share some of the work that we've been working on for almost a decade with regards to the standards development. So I will share my screen. Let's see. All right, am I presenting now?
Yes, you are. If you can just
okay.
Put it in.
And then, just give me a second. Actually, let me. Okay. I'm going to take my headset off here, if that's okay, and then I'll share. Let me see. Okay. All right, and I'll put it in presentation mode. Maybe. Right.
Doug looks good. Your voice goes out in a little bit. I'm not sure if that you change mics or.
Want to change the setting?
Yeah, I can hear you. We can continue. Yeah.
Okay. Okay. Very good. All right. Okay. So first off, I want to just recognize everybody that has contributed to this effort. Even the listed authors here doesn't cover everyone. I'll point out that there's key organizations involved, both the organizations and their members. That's ASTM International, the Aerospace Vehicle Systems Institute, and the Consortium for the Advancement of Shape Memory Alloy Research and Technology. And I'm sure a lot of these folks y'all have worked with or are even on the call today. And it really does take a large group of academia, government, and industry to come to develop standards and even more difficult to come to consensus a lot of times. And we'll note that these are consensus documents. They have inputs from this very broad community. All right. So I'll just start off a little bit talking about why shape memory alloys, and I think also too, a lot of folks on the call realize why we work with these alloys, but just kind of speaking to it from my perspective is an aerospace perspective, and we look at using shape memory alloys as an enabling actuation technology where we get reduced size and weight, high energy density actuation, the ability to work in harsh environments, integration advantages because of that energy density and ability to work in harsh environments. We could often put these shape memory alloy components as actuators into places where we otherwise wouldn't be able to. We can take advantage of passive and environmental actuation and also get multifunctionality because of that. We do look at a broad range of applications, everything from actuated wind tunnel models to deployable vortex generators, span-wise adaptive wings. We have a pretty broad portfolio. Shape memory alloys, they can operate in different forms, tension, compression, torsion. They're pieces of metal, whichever way I deform them and heat them, I'm going to get that shape recovery. And then also more recently, a lot of the work, we've been doing quite a bit of work coming from Othmane's group and a few others, but really the ability to tailor the alloys for specific applications through chemistry and processing. We now have a lot of control over the performance and the transformation temperatures with these systems, and it's really enabling even more applications or accelerating some of the applications that we've already had. So why do we need standards? So as I mentioned on the previous slide, shape memory alloy is a very promising application for a lot of aerospace applications. And standard test methods are essential for the development and the acceptance of the technology. So we need to be able to control everything from the raw material up into the actuator component, from the wrought material to processing in a bar, into tube, then testing it in ways that are relevant to our application. And then we're able to take this quality control, the data coming from the test methods, we're able to inform our design and tools and analysis. When we put a component into an application, we know how it's going to perform. We know that component's pedigree, and we're able to repeat this every time as we work towards application. It was about 10 years ago at the time, there wasn't really any standards available specifically for shape memory alloy actuation. There was quite a few that had been developed in the 90s and 2000s for the medical community, but this was relatively a new area for us when we started at about 2014, 2015. All right, so with regards to motivation, also speaking to this from the aerospace perspective, however, this would be common in other industries too. In aerospace, especially in aeronautics, we have a pretty high bar, and so that's set by the U.S. Code of Federal Regulation Title 14, that we need to establish airworthiness certification for materials. It needs to be established on the basis of experience or tests. We need to conform to approved specifications, and that's what we're talking about today, test methods that ensure the material has the strength and other properties assumed in the design data. And we have to do this enough. We have to do enough tests in order to build confidence, to build statistical significance in order to trust those design values. I'll also note that the FAA does not tell us how to make a test method or a material specification. We have to do that on our own, and we have to show them that that is sufficient. All right. So with this in mind, we formed a task group specifically for SMA for actuation. This group was formed about 5 years ago. These efforts started before we formed this group. However, we got to the point where our portfolio of test methods has grown large enough where ASTM suggested that we form our own task group. And the scope of this group is to characterize the thermal mechanical behavior and material properties of shape memory subject to the thermally induced phase transformation. The test results support material and evaluation of actuator design. So scope is focused on actuation and the thermally induced phase transformation. We started off, and I'll talk more about each one of these test methods in detail as we kind of move through the presentation here. But the three in the middle, we started off with E3097 and E3098. More recently, we have E3414, which is constant torque thermal cycling. And then we have two more tests, one material specification that's here on the left, under development by our colleague Dean Pick is leading that effort in the CASMORT design working group. And then on the right here, we have constant force controlled repeated thermal cycling. This is like a fatigue test method for shape memory alloys. And note the process flow indicated here from left to right. Although we started with the test methods, it's really that material specification that's the building block for everything. I'll explain in the next few slides why we started with the test methods as kind of being the building blocks. However, you need to be able to control the material before you even get downstream as you work into the test actuation relevant test methods and fatigue test methods. So, all right. So current published standards. The first one we went after was E3097. This is the standard test method for mechanical uniaxial constant force thermal cycling. And this is one of the most fundamental responses for shape memory alloy actuation. So here we load a specimen, and we heat a specimen, and then we load the specimen, and then we cool it, and then we heat it again. So it's the response of the shape memory alloy material under load gives us the actuation strain, the residual strain, and the transformation temperatures of that material being thermally cycled under load. The second test method is uniaxial pre-strain and thermal free recovery. This is if I were to take a piece of shape memory alloy, load it, unload it, and then heat and cool it and watch its free recovery response. Also one of the building block responses for shape memory alloy actuation. A little bit more recently, and driven by one of our commonly used forms is shape memory alloy torque tube actuation. So a lot of the benefits on the first slide, with the additional benefits of having a tube, we can have a rotary actuator that has high energy density that I can integrate into a hinge line. It's scalable. Unlike wire, it has bidirectional actuation, so I could put two-way shape memory effect in there and get, for example, flat movement up and down. And it has a lot of applications that we care about. Here I'm showing ones for aerospace. So the actuated wind tunnel models, we said adaptive trailing edge here that we tested in flight. So it's a highly valuable mode of actuation that we could take advantage of with the shape memory alloys. But it also too doesn't have any standards. So the third test method we published is constant torque thermal cycling of cylindrical shape memory alloy specimens. And here we essentially, it's a direct translation of E3097, the constant force thermal cycling test method, except we're looking at shear strain instead of strain. So shear strain temperature space. And when you perform this test, you'll see that essentially the footprint of the response is essentially the same. You generate hysteresis loops. You could take your four transformation temperatures off of these. You could generate them as a function of shear stress. There are a lot of details though associated with that translation. Anybody that does material testing here, so it did take a few years to write this test method. So we needed to take into account the specimen requirements, right? So if I'm in torsion, right, I'd prefer a thin wall tube. Do I want to limit the scope to just thin wall tubes? What are the testing differences? How do I grip it, heat it? How do I sense torque, right? How do I sense torque locally? And so all of that we had to work on, and that was now captured. That's now captured in the test method E3414. All right. So those are the ones that are published. We're not done yet. We're still working. So shape memory alloy material performance is extremely sensitive to composition, purity, processing, and test parameters. So I'm using nickel titanium hafnium 20 here as an example. We could see here in the plot on the right, these are fatigue cycling test. I have here 4 different melts. We targeted the same nominal composition. Nickel 50.3, Ti 29.7, hafnium 20, and just very small differences in nickel content and material cleansingness will produce very different results. So you could see here 4 different melts having a very different response, and we were targeting the same exact processing parameters and composition. If we look to the plot on the right, we can see here now we've taken 1 melt and we're testing it under 3 different upper cycle temperatures, 350 degrees C, 300 degrees C, and 250 degrees C. And you can see here now that there's a significant influence of the upper cycle temperature on the fatigue life in this material system. So what does that tell us? We need material specifications to control the raw material, and we need test methods to control the testing relevant to actuation as we cycle these materials to life. So these are the next 2 pieces of work that we're focused on. So first off, and I borrowed a few slides here from Dean Pick. He's been primarily leading this effort. But the first one is just taking a look at available material specifications for shape memory alloys. So there's really one available, that's F2063. It's focused on binary nickel titanium and medical applications of binary nickel titanium. So doesn't include additional alloying elements. There's no grading by transition temperature. It doesn't take into account hysteresis, thermal hysteresis, or actuation strain. And it does take into account quality, but being able to grade quality, there's one quality grade, and it's pretty high quality. So F2063 does produce really good nickel titanium, but there may be scenarios, right, where we want to maybe accept lower quality grading, right, because we might not need that high of level for our specific application. I'll note just here at the bottom, I know I'm using the ASTM designations quite often. That becomes maybe bad habit within the standards community. But I will note F2063 is the material specification for wrought nickel titanium for medical devices and surgical implants. So great. Okay, so just maybe a few more slides on where we're going with this material specification. So the first one would be looking at the first slide here looks at material specification grading, where we could grade by alloying component, and then the subgrade would be the transformation temperature, and then the subgrade would be material quality. So this allows us to set different grades for transformation temperatures and material quality. Essentially broadening maybe F2063 so that we can expand it to materials for actuator applications that could have varying transformation temperatures and varying quality grades. All right. And then also want to note here that we're also allowing for ternary alloys, so going beyond just nickel titanium. So I showed the example of nititanium 20 on the previous slide. We can also see a nickel titanium copper system here. We don't know all the grades that we're going to, we have a few in mind that we're going to consider. It's not completely locked in yet. But we also are writing this in a way so that if we were to bring out a version of it in the future, right, an update, we can add additional alloying systems to it. And we kind of are leveraging the way that titanium alloys, conventional titanium alloys are graded within ASTM standard specifications. All right. So grades are organized by austenitic temperature, austenitic start temperature. F2063 specifies AS as a requirement. However, we also want to expand to the other transformation temperatures because we care about hysteresis through the thermal cycle. And note that they're just references here. Because it does become quite difficult to make these a requirement. Difficult to control, but we want to keep them in there as a reference so that we know what we're going after. And then the last one is last slide here talks about material quality. So micro cleansiness, considerations for include porosity, non-metallic inclusions. And this is all of this I'll note is a work in progress. And my colleague Matthias here will actually talk a little bit about inclusions test methods in the next presentation. In his presentation, it's current need that we have between both of our communities and both of our sets of test methods. All right. The last test method I'm going to talk about here is constant force repeated thermal cycling. This is like a fatigue and failure test method for shape memory alloys. However, we're reluctant to call it fatigue or failure method because the objective here is to address failure of the material's ability to function in actuator applications for the required life. So you could have conventional failure. So I'm going to take a shape memory alloy, I'm going to thermally cycle it under load, essentially taking E3097 and repeating it until it meets some sort of stop condition. Now, and with shape memory alloy actuation, we could have failure because we evolve outside of our actuation range, for example, right? So that's not traditional failure. Or fatigue, right? But we have to, we want to consider that and quantify it. So we are developing those definitions as well within this test method. So for example, structural fatigue, right? This is our conventional fatigue and fracture. So process of progressive, localized, permanent structural change occurring in a material that may accumulate in cracks or complete fracture. We're also considering functional fatigue, right, which is the deterioration of the degree of transformation properties. So it could be reduction in actuation strain, shifted transformation temperatures. This test method, we just finished it. It is in ballot right now with ASTM. And ballot will be complete by the end of the month. And this is the opportunity now for those members of the E08 community who currently hosts this test method development in the subgroup have the opportunity to go in and comment or vote down the test method if there's any reservations. And so it's in that process right now. So hopefully next time I talk to this group, we have an update there. Great. All right. I'm at about the end of the presentation here. I'm going to just bring this last slide up, and I think it will kind of transition into Matthias's presentation. But recently we published this article in AMP magazine, Advanced Materials and Processes, under the SMST Newswire. Where we highlighted all the ongoing work between the medical device nickel titanium shape memory alloy development efforts under F04, and then the ones that we're working on that I just talked about, us being shape memory alloy for actuation, and where we have some overlap in the middle, including that new inclusion test method, which is being actually developed under ASTM E04. So, all right, and with that, I know we started a little bit late, but I think we're on time here. I'll leave it up to you, Othmane, if we want to take a couple questions or press on. So thank you for your time.
Thank you very much, Doug, for this wonderful overview here. I think we will, correct me if I'm wrong, Mirsad, but we'll leave questions for last. We can take questions now for Doug.
Yeah, if people wants to write if they have any question, they write it also in the chat right now, and we can ask the question right now. But I do not see any questions.
Okay, very good. Okay, so in that case, let's since that's a good segue, Doug, into Matthias' talk that ties into medical. Let's go through Matthias's talk, and that way we can leave some time at the end to answer questions that came through the chat or through emails, and we'll go from there. So with that, Matthias, if you are ready, the floor is yours.
Thank you. I'm ready, and I hope you can already see my screen.
Yes, we can.
Okay, great. Then we can get started. So first of all, thanks to Mirsad and you, Othmane, for the introduction and the opportunity to present here as part of the Smart Webinar series. And as Doug has already gave you an excellent introduction to the world of standards in the Nitinol actuator realm, it is my pleasure now to continue with the medical-related Nitinol standards. Okay. First of all, I would like to give you a graphical overview of the standard landscape we currently have regarding NITI-specific standards applicable to medical materials and devices. You already saw this kind of bubble landscape from the paper. Now, this is an extract for the medical devices. As you can see here, those NITI standards reside on the American Society of Testing and Materials, EA's international side of standardization, but they are split among several committees. Let me begin with the F04 standards. And these are the Medical and Surgical Materials and Devices Committee. And there are two subcommittees hosting those documents. F0412 is responsible for terminology and specifications, shown here in blue, and F0415 for the test methods. These are marked in green. The two specs we currently have, and that Doug has already pointed out, is the F2063 for rod NITI and F2633 for tubing. Now, F2063 is under revision. However, there are two new standards in development, which you can recognize by the WK designation, which stands for work item. It's a temporary designation for work item at ASTM. In this case, the new specs don't have an official ASTM designator yet, as they are not published yet. So the WK numbers will be replaced by an F designation once they go live. The first new standard is a rod wire spec, and the second one is about rod plate, sheet, and foil. So these will complement the NITI semi-finished product forms marked here in a lighter blue for better visualization. Moving on to the test methods under the jurisdiction of F0415, we can see that there are three standard test methods for Nitinol, namely the DSC and the BFR standards. So differential scanning, calorimetry, and bending-free recovery methods for determining the phase transformation temperatures, and F2516, which is a tensile test standard for Nitinol. Now, that what's new is a work item for NITI standard in committee E04 on metallography, and the corresponding subcommittee is E0414, which is on quantitative metallography. The new work item has the designation 84104. It is a new test method for inclusion analysis in Nitinol that Doug already pointed to, and it's seen here in a light green color. I would like to explain the importance of standards in the medical device community by walking you through a use case of a cardiovascular prosthesis. If you take a look at the table here on this slide, in this case, as a medical device manufacturer, you have to specify the raw material, just as in the aviation industry. You are going to use to spec this to your supplier. So this includes, for example, the chemical composition, the porosity, the inclusion content, grain size, phase transformation temperatures as the most important ones. And secondly, you are most likely not using niter in an ingot form, so there's a need to specify the semi-finished product you need for manufacturing of your medical device. And this again includes coming up with specifications for a list of properties requiring corresponding test methods as listed in this table. Again, the vast majority of these standards are ASTM standards, and I will try to explain the reason for that on the next slide. When developing a medical device, like in this use case, a cardiovascular prosthesis, there are many device-specific standards which have to be applied for a successful submission to a notified body to eventually receive market approval. In the vascular interventions world, you can see that there is an ISO umbrella standard as an overarching guidance standard. ISO 25539-2 is part of a series of standards, with -1 for endovascular prosthesis and delivery systems, -2 is for vascular stents, -3 for vena cava filters, and -4 is for coded endovascular devices. In case of cardiovascular implants, most of the other standards, especially material specs and test methods, are on the ASTM side, like code hangers underneath the ISO umbrella document. The reason for this is the much faster revision cycles at ASTM, allowing for more up-to-date changes. Unfortunately, the standard world is not always that easy, as other medical device branches have a mix of ISO and ASTM standards and no clear structure, which led to a lot of duplication of effort in the past, as you end up with an ASTM test method on one side and an ISO standard on the other side on the same topic, which are either duplicate or, what's even worse, contain contradicting information, which makes it difficult for the users to decide which one to follow, and it will guarantee trouble during global submissions with region-specific interpretations of these standards. What you always want to avoid is a country-specific test, which is result you cannot use for another market. Ideally, these requirements would be aligned, but they are not always. That's not always the case. So we are kind of lucky with the cardiovascular device example here, as we have this informal agreement to have the more generic guidance documents at ISO and the specific ones at ASTM. Now moving on to the new standard test method on porosity and inclusion analysis of Nitinol. Where are the inclusions actually coming from? First of all, the alloying elements, nickel and titanium, can already contain impurities, but the majority of the carbon and the oxygen we have in the alloys are coming from the melting process. This is also the reason why we have to use vacuum methods to reduce the amount of oxygen as much as possible, and what makes the processing expensive. The carbon can be introduced, for example, through a graphite crucible material, and you have to keep in mind that there's a difference between the purity of the material, which is pretty much fixed after melting when you have your ingot, and the inclusion size and distribution, which can subsequently be affected by forming processes such as hot or cold working. You can see examples of the two relevant inclusion types in Nitinol in these images. We call these titanium carbides, so of type TIC, and intermetallic phases, so titanium 2 nickel, which can solve a lot of oxygen. In literature, you sometimes find these designated as oxides, although technically that's not really correct. The ASTM 2063 specifies the carbon and oxygen content for use of the material in medical applications, and you can see the boundary of the threshold values, which are 0.04 weight% for both of them. It also specifies the max inclusion size, which is 39 microns, and the expected max area fraction at a given magnification, typically 400 to 500x, and should not be larger than 2.8 area %. Now, this slide shows a solidification microstructure of a Nitinol ingot and the evolution of titanium carbides as a function of carbon content in the melt. So the two images on the left bottom of the slide show on the left hand, so the left image is primary carbides with a rather low carbon content in the alloy, whereas the nice dendritic structures can form during solidification when there is a high carbon content. At the bottom right of the slide, you see these titanium carbides can form networks in the nitinol matrix. And the left image is in the longitudinal deformation direction, whereas the other one is in the transverse direction prepared. Impurity-related secondary phases are hard and brittle and have high melting points, and therefore they represent a weak point in the material, especially under dynamic loading conditions. So the fatigue topic has already been touched on by Doug in his previous presentation. Looking at the ternary phase diagrams of nickel titanium carbon and nickel titanium oxygen, it becomes obvious that nitinol can solve a significant amount of carbon, but is forming TIC in the matrix upon solidification. And the diagram on the right shows the same for titanium 2 nickel being able to solve oxygen. That's why it is so important to control both, so that the formation of inclusions is reduced to a minimum, ideally. You can also see that both increasing carbon and oxygen content shift the phase transformation temperature downwards. And the reason is that titanium is consumed during the formation of these secondary phases, and thus the nickel content in the matrix increases. So it is not just about fatigue, but it's also about changing or achieving your desired phase transformations for your application that you have in mind. Another reason for the importance of carbon and oxygen content in nitinol is the fatigue performance, as both secondary phases are hard and brittle and can lead to crack initiation and subsequent fracture under fatigue conditions, like those frequently encountered by medical devices, which typically stay in the human body for a long time. In general, it has been found that the oxygen-rich intermetallic phases are worse than carbides. At the bottom right, you can see two fracture surfaces of nitinol wires subjected to rotary bending fatigue, where the wire is bent into an arc and rotated until fracture. Inclusions on or close to the surface can act as stress racers and can initiate cracks. Inclusions can also form what is called particle void assemblies, or PVAs in literature. They form during deformation of nitinol material, for example, when manufacturing wires or tubing, and the nitinol matrix is deformed, but the hard and brittle secondary phases break up during this process and are elongated, forming stringers in the forming direction. And in some cases, the nitinol matrix is not fully closed around the inclusions after processing, leaving these porosities close to the particles. And at the interface between the porosity and the inclusions is the highest stress location where the crack would initiate. And those cracks can connect, allowing the crack to more easily propagate through the material from one inclusion to the other. That's why it is interesting to know, for example, what the nearest neighbor distance between inclusions is. The smaller this distance is, the easier it is for the crack to propagate. And then there was a nice paper by Barahim et al. in Acta Materialia about this phenomenon. The following slides show some clinical examples of nitinol device fractures, and in this example, a self-expanding nitinol stand is shown after 9 months after implantation, and it has a severe stand fracture in the distal and a moderate stand fracture in the proximal part of the stand. And angiographically, both lesions were associated with a restenosis larger than 50% in diameter reduction. So this is dramatic for the patient, which means that the lumen is less than half of what is intended to be by actually standing this position in the artery. Another example of a nitinol stand in the popliteal artery, so this is around the knee, with severe fractures and segmentation can be seen here. It has to be mentioned, though, that many different reasons can lead to clinical failures. Besides the material quality that we briefly touched on, the device design, underestimation of the loading conditions, a huge variability of the patient population, and also complex interactions of the device with calcifications, ligaments, bones, and so forth can result in fractures. And finally, on this slide, you can observe a plain radiograph. In image A, it shows a band at the junction between a covered and an uncovered nitinol stand, and coronary 3D reformatted CT images in the images B, C, and D are showing fractures of the uncovered stand at the junction to the covered stand, with the fractured segment protruding into the lumen. And obviously, this is something you don't want to have as a patient, as it may be causing pain and the need for intervention by the cardiologist. Right? Typically, a material specification should not describe test methods. It should reference a recommended test method, though. On the other hand, a test method should not include acceptance criteria for materials. These are two distinct types of standards that are not to be mixed up. Unfortunately, this has happened in the past when those standards were initially developed. Now, why do we need to standardize the nitinol inclusion analysis? Well, you all are aware of the increasing propagation of nitinol use in industry, and it's not just limited to aviation, space, and medical, but there are many other areas where NiTi is progressing. And so is the need for specification or for specifying the material across the entire value chain, right? And I already pointed on the fact that the processing is changing the microstructure and the properties. So if you're moving on from the ingot to the semi-finished product to the device, you have to keep this into account. And also Doug has already said that there are some applications out there that may require a higher purity. There are a bunch of names on that in the community in use, like Eli, Enduro, Redox, and so forth. And the main purpose is to have a longer service life or higher fatigue safety requirements. So you need to screen the material for the right quality for a specific indication. For example, in our case, it might be a valve or a neurological device, certain pacemaker components where you have like zero tolerance for fractures. In contrast to, let's say, a peripheral stand where you can have multiple fractures without any severe outcomes for the patient. Now, F2063 describes acceptance criteria for the inclusion analysis in medical applications, but it is historically not taking newer, cleaner material qualities into account or higher risk, longer service life requirements, because those simply didn't exist when the standard was originally developed. And it turns out, insufficiently describes the test method for inclusion analysis. So it leaves a lot of room for users in how they design their test methods, and this leads to a lot of variability in the test results. And we saw it firsthand or the hard way when we try to do what we call an international laboratory study. It's kind of a round-robin test in the ASTM parlance. And we did 4 of those, trying to determine what we call a precision bias statement that basically describes how precise and how repeatable a standard test method is. So what's your expectation of the spread of data? And we dramatically failed on all 4 of those. And this was then the decision point for the working group to go separate ways between the spec and F2063 and the new test method. So we decided to take the test method specific aspects out of F2063 and write our own standard on just the method. These SEM micrographs from Peltner illustrate the evolution of material purity in binary nitinol alloys over the last couple of years. And you can see that optimized melting methods have resulted in higher purity alloys by reducing the carbon and oxygen contents, leading to fewer and smaller inclusions. As mentioned earlier, this does not matter for every application, but it is important for higher risk requirements, where the increased purity can allow for higher fatigue safety factors and a significantly longer service life. However, the need for a suitable and reproducible inclusion test method remains across the whole value chain, from melt ingot to semi-finished product all the way to the devices. We established a new working group at ASTM in EO414 on quantitative metallography, and this is a cross-industry and academia team, and not limited to medical, as the new test method is supposed to be universally applicable. So Doug, you guys will be able to use it too for your applications once it's available. And the new method consists of 3 distinct phases. So we are trying to cover the sample prep phase, the imaging phase, and also the automatic image analysis. We are allowing 2 different methods. One is using scanning electron microscopes. The other is an optical microscopy method. And initially, we are limiting ourselves to nitinol hard work material per F2063. Although we plan to expand that later, so I will elaborate on that at the end of my talk. And it is supposed to be a universally applicable test method. Now, it's also important to mention what's out of scope. And we have refrained from allowing manual image analysis methods, as this is no longer regarded as state-of-the-art. And we are also not defining any material grades like standard or high purity or class 1, 2, 3 or whatever you want to call it as we're describing a test methodology instead. And we will also not define any new acceptance criteria for specific applications, material qualities, or industries. So we will focus on the test method, actually. The following example evaluating tube half shells shows how the method and principle works and how it can be applied to screen and compare different suppliers and material qualities. In this case, tube half shells were evaluated using SEM images, and you see the sampling locations in this schematic drawing here on the right-hand slide. And then SEM images were taken using element contrast and backscatter mode. And subsequent, we did image analysis using image analysis software that can help to identify and quantify the inclusions. Automatic classification can be used to determine the particle size and area, and many additional analysis parameters like total particle area, roundness, and so forth can be evaluated. There are some commercially available softwares out there that can analyze up to 100 different parameters in a microstructure. So, moving on to the results, the following slide represents a supplier material evaluation showing the usefulness of the inclusion test method in determining equivalence between materials. Keep in mind that depending on the sample geometry, the results will not just be a question of material purity, but also of the sophistication of the manufacturing processes being applied. So as an example, supplier A could use a standard Nitinol quality and produce a premium quality tubing with superior tube manufacturing, whereas a supplier B, who has access to a high purity ingot material but has less sophisticated tube manufacturing, may result in an inferior fatigue performance of a device made from the latter tubing. So in order to manufacture a superb tubing, you have to master both the material quality and the tube manufacturing processes. And there is a huge variability out there on the market for both of those. These examples compare automatic image analysis of a standard and a high purity Nitinol material with the corresponding histograms of the inclusion distributions. You can see that the difference in inclusion size density becomes already obvious when looking at the SEM micrographs, but now with the new method, they can be quantified using the new methodology. Finally, moving on to the new test method, this slide provides an overview of the workflow of the 3 phases: sample preparation, imaging, and image analysis. Each of the phases can have an impact on the quantitative results, so we have to standardize all 3 of them. That was a learning out of the failed ILSs and F-2063. If you take a look, there are some parameters that we try to nail down to fix as much as possible and take out variability in the methods being used. As an example, for the sample prep, in the first week that the working group was trying to identify the different sample preparation techniques, we collected 13 different recipes within a week. So that already showed us, oh my goodness, we really have to standardize this. And I don't want to read through all of this, but this gives you a brief idea of what this is all about. Coming to the latest developments about this new standard test method, we had to make a couple of decisions. First of all, we decided to initially focus on testing per F-2063, although there were many ideas in the working group how to expand the method to other alloy compositions, shapes and forms, devices, and for fatigue prediction purposes. However, in the interest of time and to speed up application of this first shot, we decided to limit ourselves to the F-2063 specific testing. The draft was completed in June last year, and with initial ballot on the subcommittee level completed in mid-August. We then did something what is called the courtesy ballot. So we reached out to the user community within ASTM, so the EO8 folks from the fatigue and fracture community and the FO4 committee on medical devices and materials, and they could all vote and review the draft, and we collected the feedback, and not just within EO4 but beyond throughout the Nitinol community. And the result was kind of overwhelming. So we got more than 100 comments back from the reviewers, and this led to some substantial revisions that are still ongoing of our initial draft document. So we wrote a new significance and use section. We added an interference section and an apparatus requirements section, and also rewrote the test samples and statistical calculation and calibration section. And now we are in the midst of the procedure section. This is ongoing, so we have bi-weekly meetings where we try to do this. Now, what's good to know maybe for you folks out there is that if you are trying to develop a new standard test method, there is a requirement that you should know about. And this is that before you can initially publish such a new standard test method, you have to conduct what is called a single lab standard deviation repeatability study, which means that a single lab has to do an analysis applying the method as written. And I gave an example here in the records. And this will be published as a repeatability statement at the end of the standard document. And this buys you pretty much time. So once the standard goes live as such, you have now time up to 5 years to conduct a full interlaboratory international study. And we already found a sponsor. So Fort Wayne Metal is kind of sponsor the material for the one lab repeatability study and also the subsequent full ILS that we plan to do once the document gets live initially. So if you're interested in participating with your lab, just let me know. You can shoot me an email or get in touch so we can add you to the list of interested participants. Now, after initial publication, the working group will immediately initiate another work item for revision to establish the precision bias section and to elaborate the standard to cover semi-finished products, devices, and fatigue performance predictions, as I've already pointed out. So we will also not just look at the longitudinal preparation of material as per F2063, but we will also look at the transverse, which may be more relevant for semi-finished products and fatigue performance. Most likely, or we hope that the ILS will give us proof of data that the SEM method is superior to optical. So we will make a clear statement if this is the outcome. There are resolution issues with optical and some other aspects, like it's more prone to artifacts affecting your quantitative measurements. So we found this out in some bilateral round-robin tests we did. The outcome is supposed to be the precision bias statement, and the results will support future validation and acceptance criteria. This may also be interesting to know. So if a standard test method already includes a precision bias statement, you can use this precision and bias to develop your test method. And if you follow the standard and you can prove in your test method validation back home in your lab that you achieve a variability and a repeatability that is within the established precision bias statement, then you have validated your method and you can claim that you're in compliance with the standard. And of course, we will also include the insights we gained from the failed ILSs in F2063. It's not been decided yet if this will be a separate test report or if it will be added as an appendix to the new test method. So what do we want to expand the document to after initial publication? We will add guidance for testing and analyzing semi-finished products and devices. And we will also describe a procedure how you can use the inclusion analysis to eventually perform predictions about the fatigue performance using a methodology known from the steel industry. So we are leveraging here a little bit from the decades-long experience in steels, and this is about extreme value analysis. So a statistical method that can be applied to make fatigue predictions about service life. The second
we have a minute left here, so we would like to take some questions.
Okay.
Matthias.
Yeah. So I have another standard that I will just skip. It's about ion release testing that I just want to briefly touch on. It's F3306. We are doing an ILS on that as we speak. We have 9 labs that already reported data on this. And we are looking forward to have this available soon. So this will be added to the standards, another standard that is relevant for the Nitinol community. And this is now in statistical analysis with the ASTM ILS study group. And with that, I'm at the end of my presentation, and I hope I could give you a little overview of the medical device standards landscape, and I'm looking forward to your questions. Thank you.
Thank you very much, Matthias. Wonderful talk. And most importantly for our audience, you know who they are, Doug Nicholson and Matthias Frotscher. They both provided their contact information in this context here. And this meeting has been recorded if you would like to refer back to it and connect with the community. So we have a few minutes here just to take on 1 or 2 questions here. So one of the question is the actuator community plugged in with this inclusion standard developments to see if the hafnia, for example, and nitihafnium and other things in copper are applicable using this method or not. So this is for either one of you that can take on that question, Doug or Matthias.
I would say that we're certainly talking now. So I think we could, we could probably be more deliberate about it, right? Because we do, I think, understand very well the issues associated with nitihafnium, for example, right, and the sensitivity to inclusion content, right? And by deliberate would be more so applying that test method, even the draft test method, to our specific material systems, right, to investigate things like the lot-to-lot variability that we see, right, or the melt-to-melt variability. So I think we could certainly be more deliberate about that. But the good thing now is we are engaging, right? So the actuation community are attending the FO4 meetings. Folks from the FO4 medical device community are attending our material specification development meetings. So
yeah,
wonderful.
I can add to that quickly. So as I said, initially the test method will be focused on F2063. So we are providing for example, sample prep recipes that are applicable to binary nitinol. And if we want to add additional alloys or expand the methods beyond binary per F2063, then we will reach out certainly to the community, and we can add this in the appendix, like ternary specific preparation methods and stuff. But in general, the method is universally applicable, so it should be applicable to other applications or materials, nitinol materials, as well as it is using an image analysis method. So basically, it's image processing. Once you know how to prepare your samples and you know how to image them, then it's about image analysis, and the mechanisms there should be universal. So a different question would be, are we interested, or do we need to know inclusion-specific countings? For example, do we want to know like an intermetallic hafnium phase and separate these from, let's say, titanium carbides or oxygen-rich intermetallic phases? So do we want to separate those inclusion types? And at the moment, we are not doing that. So we are basically counting porosity and inclusions as one, and then we also don't differentiate between carbides and oxides. It's just a matter of what kind of impurity you have in your material and what's your acceptance criteria for a specific application at the moment.
All right. Thank you for your answers. And since we started a few minutes late, we'll take one or two more questions just to give you the full hour. There's a quick question here. Is there anything to learn from other standardization bodies like VDI in Germany, for instance, or GIS in Japan? Have they crossed this bridge already, or this is one of its kind, first of its kind? And this is a VDI applied to actuators, and GIS applies to all of them. This is the Japanese standard, for example, nitinol.
Is this a question going to Doug?
Either way, so VDI applies to actuators and GIS applies to medical.
Doug, you want to start?
We lost audio, Doug. We lost your audio. No audio.
No.
Okay. Matthias, perhaps he can give it a shot while he works out
his
audio.
Yeah. So the GIS standards in Japan, and then there are others like in China, and you have region specific or country specific standards. Typically, the regulatory agencies tend to accept international standards like the ISO standards. ASTM is also an international standard that is widely applicable and it's not limited to the US or the European markets. So when we are going to the Japanese market with our products, we are applying ISO and ASTM standards as well. Of course, we are aware of what's out there in the GIS standards, but typically they're not even translated into English. So it's kind of difficult to get your hands on, and also the global acceptance is difficult. What you always try to avoid as a manufacturer is to have country-specific tests. so that you do a test, let's say for Japan, but the results of this test, it might be, let's say, a fatigue test that takes a very long time and is very expensive, but you cannot take these test results and submit them to another country like the US for submission on this market. So you have to build a machine just for one country to get to sell your products in this market. This is something that you usually try to avoid. The purpose of standardization is to have a universal test method that is applicable everywhere, that is accepted everywhere, and this is sometimes the challenge, the acceptance in regional markets.
Well, thank you for that answer. And Doug, is your audio back? We have a question very specific to you, to aerospace community.
Can you hear me?
I can hear it. Good, yeah. Perfect.
Okay, all right. So the question's in the chat, right?
Can you see it? Yeah. So the question for the audience that doesn't see the chat is the current standard, this is specifically for the actuator one, is the current standard for material characterization already incorporated into the construction codes and standards? You probably know what this is from Andre Setiawan. Those of us in aerospace understand these codes, but maybe you can elaborate there. And this will be our final question for today.
So they are not, right? That material specification that I spoke to is not even published yet. But I would note that we are borrowing frameworks, right? Successful frameworks from conventional material systems and standards. So if we're not starting from scratch, right? Like, so I mentioned the titanium alloy test methods, for example, right, where you'll have titanium grade 5, right? We know is Ti 64, for example, a commonly used alloy, and we're developing our material specification framework such that it does this. Now, I don't know. You know, in the future, I think it would be ideal to have these in standardized codes, standardized designations, but we have to start with the building block, and that's where we're at right now. So,
all right. Well, with that, I would like to thank our speaker. Thank you so much for being here with us. I would like to thank our audience for being with us, and hopefully this was useful to learn about standards. Like I mentioned earlier, this will be recorded for future references. And I want to thank AM Smart and CAD Smart for sponsoring this event for us. Mershad, the word back to you.
Thank you, Othmane, and thank you also the speakers, Matthias and Doug. It was very interesting. Maybe it is also very interesting for the community, NITI. I'm pretty much sure people also later have a chance to see and watch this video and learn from that. I want to just mention the video is going to be shared in the YouTube channel of the AM Smart group, and then also if you want to have also more information about future webinars, please follow our LinkedIn. And with that, I would like to thank everyone and have a nice day.
Thank you.
Thank you.
Bye.
Bye.
Bye.